Welcome back. We're doing Bayesian linear regression, and in the previous couple videos, we started out by defining just the standard linear regression model, and then we put this prior on the parameter vector w, and that was the first step to being Bayesian. And then in the second key step of being Bayesian, we were just applying the rules of probabilities, and we were doing that first by computing the posterior distribution on W given the data. And we found that it was this nice normal distribution, and we were able to analytically get the form of the posterior distribution, and it had mean, mu, and covariance matrix lambda inverse, or precision matrix lambda, for some mu and lambda. And for what we're going to do next, it turns out that it won't be particularly important what they are, but you can go back and look at those if you want. And so what we are going to do next is to continue being Bayesian. We're going to compute what we really want, the predictive distribution. And in order to say, so what is, well, the predictive distribution is the probability distribution over a new y for a new x given the data. And now, to be confusing, I'm going to use the same little y in this video, but for a different purpose. In this video, I'm going to use little y to denote the value of a new y here, which corresponds to a new little x in RD. So we're going to get a new little x, that's going to be this one here in RD, and then we're going to introduce a new random variable, just capital Y, which will also be conditionally independent of all the others given W. And it will have this same sort of distribution, but now it's going to be just x here instead of xi. Okay, so hopefully this won't be too awfully confusing. I think you'll be able to keep track of it all. So before we were using y for the vector of little y's, and now y is a value that this random variable y may take. Okay, so let's compute this thing. So let's compute this Okay, before we get started, let me say that usually when people compute this distribution, and the posterior sometimes, they use a general result for what are called linear Gaussian models, or the linear Gaussian model. But rather, I wanted to make these videos self-contained, so I wanted to compute this directly without referring to some more general result. And I think it's very instructive, even though this is a somewhat lengthy calculation. It's fairly straightforward, and I think it's very instructive to see why it works. I mean, to really understand it, to get down to the nuts and bolts and understand why it's possible to do this exact inference in the Gaussian system, with the multivariate Gaussian. So with that sort of disclaimer, we're ready to compute this predictive distribution. All right, so let's do it. So here we go. Well, this thing first let's integrate out our parameters. That's what we always do when we're being Bayesian, as they say. So this is equal to the probability of y integrate over. So we're going to integrate over the probability of y given x, d, and w times the probability of w given x and d, integrating with respect to w. And this first part, now this is sort of maybe a little bit confusing. The x's, this x here is not random. This is purely a notational device. We say conditioning on x purely as a notational device to indicate that this is the value of x for which the distribution of y corresponds. So this equals, so the y is conditionally independent of all the other y's given w. That was our model, part of our model. So this equals the probability of y given the data, or not given the data, given x and w. And for the same reason, since x is not random, a sort of this there's no capital X corresponding to this little x. This is just a notational device. This is equal to the probability of W given the data. If you wanted to make this notation be exactly correct as a conditional probability, you could put just a probability distribution on some capital X that was to make it identically equal to little x, and so on and so forth for the other xi's. All right, so with that out of the way, now we can rewrite this. This one here, our model on y is normal, so it's a normal density. We'll use this shorthand, normal density on y with mean W transpose x and variance. What was the variance? The precision is A, so the variance is A inverse. And this is just the posterior on W. So that's a normal. Remember we found, oh, right, here it is. The posterior. Normal, mean mu, covariance, lambda inverse. Lambda is the precision matrix. Integrating with respect to W. Okay, so now we can start computing. We can plug in the expressions for these, so let's do that. This is proportional to e to the minus a over 2 y. Now y is a scalar value now, not a vector. Y minus W transpose x squared. And this one, this is e to the minus 1/2 W minus mu transpose lambda W minus mu. And the constants drop out because they don't depend on W. This is proportional, oh, not W. This is proportional with respect to y. The constants do not depend on W, right? This one just involves A, and this one just involves lambda. They don't depend on W or Y, so they drop out. We had to make sure they didn't depend on W because we're integrating over W. Okay, and now let's see, what do we want to do? Let's go ahead and multiply this out and pull these two exponents together. So this is equal to, we'll just multiply this out, minus a over 2 y squared minus, let's see, 2 W transpose x times y plus W transpose x squared minus 1/2. And yeah, let's go ahead and multiply this one out too. So this is W transpose lambda W minus 2 times, how should we do it? Let's do W transpose lambda mu. Lambda equals lambda transpose because it's symmetric. Precision matrix is always symmetric. Plus mu transpose lambda mu. Okay, all that in the exponent. Right, let's see, is that right? W transpose, yeah, lambda mu. Okay, and now, right, so this part doesn't depend on y or w, so let's go ahead and we can drop that out. Let's say this is proportional. We can just forget about that part. And now we want to work with this exponent. So let me pause for a moment here and tell you our general strategy for this calculation. So at this point, you can start to see that this is a quadratic. This is going to be a quadratic form, or we can factor it to make it into a quadratic form in W. Well, W minus some mean or something, but it's going to be quadratic in W. And so this our goal is to express this. So let me put this as an aside here. So our goal is to make this equal to an integral of a normal over W with some parameters times some function of y that does not depend on W. And then, since this does not depend on W, it's a constant, comes out of the integral, and this integrates to 1 because it's a density over W. So that will become just g of y. And then our goal is to express this, well, maybe I should say proportional. Maybe this should be proportional to or something. To express this as proportional to a normal over y with some parameters. So this is what we're shooting for, just to give you the big picture of where this is all going. All right, so the next step in this general plan is to get this in the form of a normal over W. And how are we going to do that? So let's make a little room here. Let's focus on the exponent. That's the part that really matters. And let's pull out the minus 1/2. There's a minus 1/2 on both sides. So let's go ahead and pull that out. So the exponent, what we're left with, let's see, we can multiply, go ahead and multiply a through. So it's going to be a times what's inside here. Oh wait, I missed a parentheses. Sorry. I missed a parentheses right there. That's the parentheses for this one. Minus 1/2. Right, okay. So this is going to be a times what's inside here. So this is ay squared minus 2w transpose xya plus a times w transpose x. And let me go ahead and write this, I'm thinking ahead here, in this form, x transpose w, because this is a scalar, so we can just transpose it. It's equal to its transpose. This is getting things in the form w transpose something times w. That's what my thought process is there. And this part, well, we just pull out the minus 1/2, and we get w transpose lambda w minus 2. Yeah, it's minus, right? Yeah. Wait, minus. Right? No, this becomes a plus. I hope I don't make any mistakes here. Right, so we pulled out the minus 1/2. This is right. We pull out minus 1/2. This is plus minus 2 w transpose lambda mu, and we forget about that part. Okay. Now what? We want to get this right. We want to get this in the form of a Gaussian. So let's go ahead and pull together the like terms, the quadratic terms and the linear terms. So this is, let's pull together the w transpose terms. So this is, if we look at this one, we pull out w transpose, we get axx transpose. And then we pull out w transpose from this one, we get lambda. Pull out w on the right from both of them. That takes care of those two. Now let's pull together these two terms, the w transpose terms. We get minus 2 w transpose times xya. X is the only vector here. Y and a are scalars. Plus lambda mu, right? Plus ay squared. Is that right? That's that part. That's that part. Yeah. Okay, out of time for this video, so we'll be back and we'll continue computing this predictive distribution. See you soon.